Chapter 12, Understanding Research Results, Description and Correlation. Disclaimer. This is a long list of learning objectives, and it might just be easier to say that we're going to do a brief review of very basic statistics concepts that you probably already learned in intro statistics. And then we're going to transition into talking about more complicated statistical methods for analyzing your data. Even though this is going to be some review of intro statistics, the reason why all of this is really important to discuss in a research methods class is because if you do not understand how to properly design a study and use the correct statistical analysis for the design you plan to use, you're definitely going to be lost and will have some real problems being able to interpret your data in a way that's meaningful. So let's just jump right into it. Here are some concepts that we've already talked about in previous chapters, but we will review them here because knowing what types of variables you plan to use will make a difference in your available choices for statistical analysis. So keep in mind that nominal scales are those that don't have a numerical value, but just basically are categories that don't have an actual value. So for example, eye color is an example that we used before in this class. Even though some people might not fit neatly into a specific category very well, the purpose of the categorical system is just a way to sort of put people into boxes to help us understand the data better. Ordinal scales provide a rank ordering system from top to bottom or first to last place or whatever. It discriminates between first, second, third, and so forth, and that's the only thing that a person would be concerned with here. Interval scales are often what researchers use because it allows for more sophisticated statistical analysis because we know that the intervals between the different levels are equal in size. Similarly, the ratio scale has equal intervals at each step, but also includes an actual 0 point and not just some arbitrary zero or arbitrary group of numbers. So let's keep these facts in mind as we move forward and talk about different types of statistical analysis that we can do depending on the types of scales that we use. On this slide, we'll talk about the three basic ways that statistical results can be described. What we're focusing on here is relationships between variables. When we compare percentages, which is usually done by considering whether there is a statistically significant difference between groups. Sometimes there might be a difference between two groups, but the difference is actually too small to be meaningful. On the other hand, sometimes there is a difference between groups that doesn't look like much, but because there's so many people in the study, it actually is a statistically significant finding. Next, we can look at correlations between variables. Remember that a correlation is a measure of similarity between two variables or how much these two variables correlate. So on the previous example of comparing group percentages, we're interested in differences between groups on a specific variable. In correlation, we're actually interested in the opposite of that. We're interested in the relatedness between the variables. In the book, it talks about how there could be a relationship between where students sit in the classroom and how high their grades are on their assignments. So in this example, we would be looking for a correlation between assigned grades and location in the classroom where the student sits. We believe these variables to be related, in other words. Finally, we can compare group means, and again, this would be similar to the first example where we are looking at group differences. In our textbook, it talks about how if we had two groups of children and we were interested in whether one group would display more aggressive behaviors after viewing a certain stimulus compared to another group, we would have to look at the mean number of aggressive behaviors of both groups of children and determine whether there was a statistically significant difference. One of the easiest things to do, and every researcher really should do this, at least once they get all of their data into a computer program for statistical analysis, is to first look at the frequency distributions. What this does is it allows the researcher to look at all of the scores they're getting for every variable and to make some judgments about whether people responded appropriately or not, and also to get a handle on the typical tendencies that people might have when answering certain kinds of questions. And these can be done in various forms like pie charts, bar graphs, polygons, and histograms, depending on what kind of variables you're using. So let's take a look at what these would appear like. In this pie chart, we are only making a visual representation of the first example we went over a few moments ago about examining group percentages. We might be able to make a face valid statement about this pie chart stating that 70% of college students like to travel, whereas 30% dislike traveling. If we only asked 10 students this question, then this probably wouldn't be very meaningful. If we asked 2,000 students this question, then this would be a lot more meaningful of a difference. And here is a bar graph which essentially shows the same thing. It's just a different way of visualizing and representing the same data, which is a comparison between percentages. And notice that we have two discrete categories here of like and dislike, but there's no value assigned to either one of these categories. The term nominal data should make sense here. Looking at the frequency polygon shown in this slide, we can see that a bar graph or bar chart will be hard to interpret for this kind of data. Instead, what we see here is two overlapping lines between the example that I discussed in the previous slide of children who had aggressive behavior modeled in front of them versus children who did not. And then there was a measurement of the aggressive behaviors that those children actually showed. At face value, it certainly seems like or looks like the group of children who viewed aggressive behaviors modeled by adults seem to have more aggressive behaviors in general compared to those children who did not. This would be difficult to do as a pie chart, although I think you could probably do it as a bar chart. But the frequency polygon here makes much more sense and is more visually pleasing because it allows you to look at these discrete categories between 0 and 8. And then on the y-axis is how many times we saw that score. And if you notice, there are some kids in the model group who actually were fairly low on the aggression measure, and kids who were not in the model group, and they actually showed more aggressive behaviors. And so you can see some kind of overlap there. But what you generally see is the tendency for the kids who had a aggressive model. The distribution is much higher in terms of the average than the no model group. If you can imagine trying to make sense out of this in a pie chart, this would be a whole lot more messy. So this is where the frequency polygon can be a better way to visualize the data. As nerdy as this sounds, the histogram is probably my favorite of the visual representations of the data because it basically blends the polygon and the bar chart together so that you can see the stepwise number of aggressive behaviors shown in the kids model group. I have seen some histograms where the polygon is actually laid out on top of the histogram like this so that we can see the general trend as well as the bar chart looking aspect of the histogram at the same time. The difficulty is that when we have too many groups and too many variables with too many possible scores, it can be quite a mess to look at. And you would have obvious difficulties in interpreting that information. But one thing to think about with the histogram that would not make sense is the first example when we were just looking at the difference between the percentages of two groups. So like I mentioned earlier, the visual representation of the data should match the kind of data that you're gathering. If it's nominal, if it's ordinal, you need to really be thoughtful about what types of visual representation is going to make the most sense. I'm going to apologize in advance because I know this will seem really repetitive. No doubt that this is information that you've learned about many times in math classes all the way from junior high up until intro statistics and beyond. So I'm not going to bore you with going over these again in great detail other than to say you really do need to know the difference between these different types of descriptive statistics because The mean, median, and mode should only be used with the correct type of data that you're gathering. Interval and ratio go with the mean. Ordinal scales typically go with the median, but can also be used with interval and ratio. And then finally, the mode is the only measure where a nominal scale is used. So just keep these connections in mind moving forward. Taking descriptive statistics one step further, you should have discussed these concepts in intro statistics. But I'm going to try to give you a real-world explanation of what these concepts mean if I can, and hopefully that'll help. Variability has to do with the amount of spread among the scores in a distribution. If you look at a distribution of scores on an X and Y axis, chances are you're going to see a bunch of dots or data points scattered all over the place, and each one of those dots is a unique data point. If you try and plot a line through all those points to get an average, all of the data points would be scattered around the outline to some degree. Variability is exactly that last part, which is the degree to which all those data points are scattered away from that line. This number that corresponds to variability is usually done by measuring the distance between all of those data points and the line drawn through the middle of all of it. Sometimes this overall number is useful, but another way to repackage that number into something more meaningful is to average all of those distances between the data points and the line that goes through all of them. This is called the standard deviation. So as you can see, there is a mathematical relationship between the standard deviation and the variance. The variance is actually the squared value of the standard deviation, and the standard deviation can be calculated by taking the square root of the variance. The range of scores might seem uninteresting, just subtracting the lowest score from the highest score, although I have seen some studies where this is actually some pretty interesting information, and we'll talk about that in a later slide when it has to do with range restrictions. So you'll see why this is important. It might not seem like it's important at face value, but this can actually be an important piece of information. When we're graphing these types of relationships, it matters, like I mentioned earlier, to make sure that we're using the right kind of graph to best represent and explain the type of data that we're gathering. For example, a bar graph is better used when we have those discrete nominal categories that I mentioned earlier. But when we're using numeric values, especially when we have a continuous variable that has all kinds of values in between, then using a line graph makes much more sense. Sometimes people see bar graphs and get confused by what they're seeing because advertisers and scientists sometimes like to tweak that graph to make the differences look more subtle or more pronounced by manipulating the scale. So be sure that when you see a bar graph that you're actually looking very closely at the scale so you don't get deceived. Correlation coefficients. As I mentioned earlier, when we want to study the relative similarity between two variables or their relatedness, we want to examine how they correlate. This is where the word correlate comes from, or how much overlap there is between two concepts. From a mathematical standpoint, the statistics that we use is the Pearson product moment correlation coefficient, which is much easier to say than just, we prefer to say R, because the Pearson product moment correlation coefficient is just too wordy. So R tells us the strength of that relationship as well as the direction of that relationship. We mentioned this in an earlier group of slides, but it bears repeating again that correlational values can range all the way from -1 up to 0, and then above 0 all the way up to +1. One way that I have found is helpful to think of this is that if you think about a number line and the range only goes from -1 up to 0 and then up to +1, and all the values in between there can be a possible correlational value, and that's the only range of values that a correlation can be. So if you did some statistic and your correlation was 2, you know you did something wrong. Or if your correlation was 1.5, you know you did something wrong, because that's outside of the range of normal correlational values. Okay, so A negative correlation means that the two variables are related to each other, but are related in a negative way. So let's talk about what an example of that would look like. Typically, as elevation above sea level goes up, average temperatures go down. This is a direct relationship that occurs almost all of the time. There's definitely a link between these two variables. And as the value in one variable goes up, which is elevation, the value of the other variable goes down, which is temperature. This is the defining feature of a negative correlation. The opposite is true in a positive correlation. In other words, as the value in one variable goes up, the value in the other variable also goes up. For example, the more time you run on a treadmill, the more calories you burn. So again, there's a direct link, and as one variable increases, so does the other. In earlier slides, I mentioned this idea of looking at a y and x axis and seeing the data points that you could draw a line through. Well, this is also called a scatter plot. And this is what scatter plots can look like. These are very basic versions of it because each one only has about 10 data points in it, but this gives you an idea of what they can look like. So there's going to be some variable on axis y accompanied by some variable on the x-axis, and you will see all these data points popping up in the coordinate system. In the upper left corner, you see the label positive relationship. In that positive relationship, you can see a general trend that as the value of y increases, so does the value of x in general. If you wanted to plot a line through all those values, you would probably see a line that goes upwards from left to right. Now the opposite would be true on the graph in the upper right corner, labeled negative relationship. In this example, if you try to draw a line through all of those values, the general trend would be downward from left to right. In other words, as the variable x increases, the variable y decreases. This is exactly what we talked about a few moments ago as the defining feature of a negative correlation. Now, in the lower left graph, we see a data point scattered all over the place. And there may not be a really good way to put a line through all of that noise, but if I had to guess, the line would probably be pretty flat and horizontal. Now, if you see something like that and that's the case, then there would be no relationship because as one variable increases like x does, the relative value on y on average does not change. Ignore the fourth example here because that's supposed to be an exercise from the book and we're not going to take time to do that here. Okay, so having gone over some of the basics here, we're going to talk about some important considerations before we move forward. Taking a look at these scatter plots, we see some interesting information here. In general, with the left scatter plot, we could probably draw a line through all those data points and it would show a positive correlation between all of those values. But there's a chance that that line could be relatively weak and somewhat flat. If we look at these data points more carefully, though, we can see that the vast majority of increases on variable y don't actually occur until variable x reaches about 6 or so, as the shaded area shows. So looking at these data points more closely, what we realize is that x and y do have a positive correlation, but only when x is 6 or higher. This is what we refer to as a restricted range. In other words, when x is anywhere between 0 and almost 6, there really isn't much change in the scores on y at all. So that information may or may not be important in the big picture, but is definitely something we're thinking about if you have plans to analyze a group of data that looks like this or in any way similar to this. The truth in reality is that most of the time, real-life data does have these really strange non-linear relationships. So thinking about this kind of stuff in advance is useful. Here is another interesting thing that happens quite often in research, which is the curvilinear relationship. At the moment, I'm forgetting what example they use in the book, but I think I have a better example that will get your attention. There are a lot of people that believe that abusing stimulants will help them perform better as an athlete or on tests or whatever. And based on my understanding of the literature on this subject, this is only somewhat true. So let's pretend that variable y is performance and variable x is the amount of stimulant pills a person is taking. Initially, we can see that as the person takes their first few tablets of stimulants, the performance might increase either athletically or cognitively, but after a certain point, the positive benefits start to plateau, and as a person keeps taking more stimulants, their performance actually goes back down. Maybe they took too many stimulant tablets and they start to lose their mind, who knows? But the big picture here is that this particular type of relationship is seen pretty often in real life scenarios and is an important thing to look for. Earlier when we talked about correlation values between 0 and -1 or 0 and +1, we didn't talk about the relative strength of those relationships. As the number gets closer to +1 or -1, the relationship between the two variables is stronger. Obviously, a zero correlation means that the two variables are completely unrelated, but we do have a way to categorize the relative strength of these relationships. Small effects are near a Pearson R of 0.10. Generally, this is not really worth talking about and suggests that the relationship between variables is really minimal. Medium effects are around 0.3 and large effects are above 0.5. Similar to what I mentioned before, where I talked about the relationship between standard deviation and variance, with one being the square root of the other, the same is true here. The Pearson R correlation coefficient and the actual percentage in terms of relationships between variables. So if you square the correlation coefficient, it shows the actual percentage of the relationship between the two variables. As you can see, if you have a variable that has a Pearson R of 0.5 and you square that value, you end up with a 0.25 or 25% shared relationship between the two variables. This is what I meant when I said that small effects are pretty insignificant at the 0.10 level, because the correlation coefficient of 0.10 means that there is only a 1% shared relationship when you square the Pearson R. Hopefully that quick math makes sense. Don't think that you can't listen to these slides more than once if it doesn't sink in the first time around. An advanced concept that you might not have learned about yet is something called the regression equation. Basically, the very elementary slope-intercept formula that you learned about in basic algebra comes to bear here because it forms the basis of the equation. Making hypothetical math into a reality is what we are doing here. When we know all of the values in this equation except for one, we can manipulate the equation algebraically to solve for an unknown variable. This is the math side of it. But in psychology, we might want to know if a relationship exists between certain variables, and if so, whether a person's score on one variable is related to an outcome behavior or a second variable. If so, then we can make some predictions about what will happen if their score on one variable changes. So let's turn this into an example. You may have heard of the concept of risk assessment. If we know that a relationship exists between a person's score on a domestic violence risk scale and the likelihood of acting out violently, we can make some predictions about people's behavioral likelihood based on those domestic violence scores, at least the people who take the risk assessment. So, if a person scores highly on a domestic risk assessment, the probability of a violent outcome is much higher. If the domestic violence risk assessment score is low, then the probability of acting out violently is much lower. All this time, you've probably been wondering why you even learned about basic algebra and how you would ever use it in real life. Well, here it is. This is what regression equations are designed to do. They use a score on one variable to predict a behavior or some other type of outcome. The mathematics we use in regression analysis is based on the slope-intercept formula, also called the general linear model. And this is probably the simplest version of regression that we can do, but what if we wanted to learn how to predict an outcome based on more than one thing? So for example, what if we wanted to predict career success based on a combination of GPA, SAT scores, and undergraduate academic performance? A multiple correlation and regression model would help us understand the extent to which GPA, SAT scores, and some other form of undergraduate academic performance might all play a role in career success, including which factors are stronger predictors of a positive outcome and which might be weaker predictors. Earlier we talked about using the R as a Pearson product moment correlation, but when we do multiple correlations we use the capital R. So please make sure that you don't get those confused. In an earlier group of slides I talked about how third variables can be a real problem. For example, I used the relationship between ice cream sales, homicides, and time of year, explaining that in summertime both homicides and ice cream sales tend to go up. The book gives a similar third variable problem, but also gives you a solution for how to anticipate and deal with this problem. The solution is a mathematical concept called partial correlations. Basically what this means is that we can mathematically subtract correlations that might be interfering with a different correlation that we're interested in. The book's example is really interesting. The book says that in a hypothetical study between the number of bedrooms a person has in their home and cognitive performance, there is a positive correlation here, which suggests that on its face, the more bedrooms that exist in a person's home, the higher their cognitive performance is going to be. However, the researcher also believes that this might be affected by social class, since it's only logical that people with lower incomes might have smaller homes and fewer bedrooms. Okay, so in the example on the left, we can see that there is an extremely high correlation between the number of bedrooms that a person has in their home and social class. This means that as social class increases, so does the number of bedrooms. The same appears to be true for social class and performance, meaning the higher social class a person is in, the more likely they are to have high cognitive performance. So from a mathematical standpoint, and we're not going to get into the details in this class about how to do it, it's just a concept that you should start thinking about, is that we can subtract out the correlations between social class and bedrooms, as well as social class and performance, and then look at what's left over as the actual relationship between number of bedrooms and performance on a cognitive test. From a mathematical standpoint, you can see that the partial correlation between bedrooms per person and performance in the left-hand example is actually very small, meaning that social class almost entirely explains this relationship between number of bedrooms and performance. But what if the opposite was true? If we studied this relationship and the results were different, showing that the number of bedrooms a person has wasn't strongly related to social class, and that social class also wasn't strongly related to performance, well, we would find that the relationship between number of bedrooms in the home and cognitive performance would still be very strong, and that social class would have almost nothing to do with it. Again, this is just a hypothetical, but it is a way to sort of view visually for how we can use mathematics and statistics to account for third variables and then make adjustments so that we can try to figure out what's really going on behind the scenes. And again, this is only the case if you actually measure the variables. If a researcher suspects that a third variable is out there messing with these relationships and they don't measure it as part of the bigger study, then they have nothing to mathematically subtract and get that more pure picture that they're looking for. A very new and complicated way of combining regression models with correlation statistics and adapting it in a way that helps us approximate causal relationships is this concept called structural equation modeling. In this extraordinarily complex, and I actually taught a lab on this many years ago, so I can definitely tell you that for this class it is significantly beyond the scope of what we're talking about here. But it's in your book, and it's two important pieces that I want you to walk away with as you advance in your understanding of research methods and statistics. Generally speaking, correlation does not equal causation. Even though we can make some predictive statements with regard to the use of regression models, we still can't authoritatively say anything about causation because we can never fully anticipate third variables. And unless we're using a true blue experiment, we're going to fall short of having the authority to make those kinds of statements. But the closest that we can come to is through using a software package that allows us to use very high-level statistics and modeling that can assist us in making some approximate statements toward causation. So let's look at the next slide and get an example of what this might look like. In this graphic, we can see that there are positive relationships between a person's attitudes about drinking alcohol, their views about subjective norms, and their perceived level of behavioral control, all as they relate to the intention to consume alcohol. In looking at this model, we can see that there are fairly strong correlations between attitudes towards alcohol and intention to consume alcohol, as well as the person's subjective norms with regard to drinking alcohol and their intent to consume it. However, there is a non-significant relationship between a person's behavioral control and their intent to consume it. Rather, there is a modest relationship between their behavioral control and the actual behavior. But the strongest relationship appears to be between a person's intent to consume alcohol and their overall behavior. So a statement that we might make about this model is that attitudes and subjective norms play a strong role in the person deciding or maybe showing some intent to consume alcohol, and that their intent appears to have nothing to do with their behavioral control. Moreover, their behavioral control is actually a significantly weaker factor in their overall alcohol consumption behavior than their intent to drink it is. So as you can see here, this model seems to explain quite a bit more about the relationships between these different variables than an ordinary statistical analysis might do. And this is why, for the purposes of this course, we're just explaining what structural equation modeling is and sort of opening your eyes to how statistics and research methods can help us explain complex relationships and complex concepts all at the same time. That does it for this group of slides. Thanks for listening.